Alright, let's work some problems involving orthogonal sets and orthogonal matrices. We're not going to go nearly as in-depth as we did in the actual theory videos, but we'll actually be able to work out some problems. So let's start with this one. This is problem 3 from the book. This actually is related to problem 2 that's on your homework. In problem 2, we had we had 3 vectors, though problem 3 is not going to use u1. So u2 is 2/3, 2/3, 1/3. u3 is 1 over square root 2, negative 1 over square root 2, and 0. So these are two vectors in R3, and in problem 2 you show that these are not only orthogonal to each other, but they are unit vectors. That they form an orthonormal, or with the u1 in that problem, they form an orthonormal basis for R3. But here we're just going to take two of them, and we're going to say that we have a subspace S that is the span of these two, that they form an orthonormal basis for S. Sorry, U2, U3. We are going to project this vector x onto this subspace. Now, we have a formula for that. So our projection P is just going to be, we're going to call it C2 to fit with the U2 that we're going to be dealing with, plus C3 times U3, where the C1 and C3, or sorry, C2 and C3 come from taking the inner product of x with each of our basis vectors. This comes from our theorem. So all we really need to do is look at the inner product of x with u2. But remember, this is just our normal scalar product. We're not doing anything really too fancy here. So we're taking the scalar product of 1, 2, 2 times this u2. So 2/3, 2/3, 1/3 transposed. And we multiply it out. We have 2/3 plus 4/3 plus 2/3. Actually, let me go ahead and write that. 2/3 plus 4/3 plus 2/3. And we have a grand total of 8/3. What about C3? C3 is the inner product of x with u3. So same process. Except now our u3 is 1 over root 2, negative 1 over root 2, and 0. This is going to be a little bit more fun because of all the roots, but we have 1 times that, so we have a 1 over root 2. We have a 2 times that, so we have a minus 2 over root 2. And then, of course, the last one is 0. So overall, we actually just get negative 1 over root 2. So this p, actually, let me move the p down below. So we're just going to take these coefficients that we found and multiply them to the vectors. So C2, again, is 8/3, but it's going to be multiplying the vector 2/3, 2/3, 1/3. And then we have a minus 1 over root 2 times the vector 1 over root 2, negative 1 over root 2, and 0. And then we actually get to multiply that out and add these together. We have 8/3 times 2/3 minus 1 over root 2 times 1 over root 2. So actually the root 2 here makes sure that we don't have to deal with any roots in the overall thing. So what is 16/9 minus 1/2 is a 23 over 18. Then we have a 18/9 then plus 1/2. That's actually going to give us a 41 over 18. And then finally we have an 8/9 and nothing, no contribution from the other one. Alright, so this is our P. This is our projection onto S. We want to show that not only is, well, we want to find out what p minus x is, and we want to show this orthogonal to u and u3, or u2 and u3. Okay, so let's start with finding x minus p. Remember, x is 1, 2, 2. And we're going to subtract this up here. I'm not going to write that out again. But we have 1 minus 23/18. It's going to be... Oh, wait. Okay, sorry. They wanted... I think they wanted... Yeah, they want p minus x. So the other way around. So now we're taking 23/18 and we're subtracting 1 from it. That's going to give us a... What was it? 5/18. Then we have 41/18, but now we're subtracting 2 from it. So we get, well, we actually get another 5/18. And then finally, we have 8/9 minus 2. We get a minus 10/9. So p minus x is this vector here. What is the inner product of that with u2? So remember, just taking this whole thing, multiplying it to this vector here. This is the normal scalar product, so we're really just going to take 5/18 times the 2/3 plus 5/18 times another 2/3. But then we have this minus 10/9 times a 1/3. And we get to actually figure out what all this stuff is. So for one thing, the 2's in these 2/3 will actually cancel out the 2's from the 18. So everything is just over 9 and 3. So everything will be over 27. But then what are we left with? Well, the 2's already been taken care of. So we have a 5 plus another 5. But then minus a 10. And hopefully it's not too hard to see that the numerator here is 0. So we get 0 overall. So p minus x, like we expected, is orthogonal to u2. What about u3? Well, same process. 5/18, but this time times 1/√2. Then we have 5/18, but this time times negative 1/√2. And then we have a 0. I'm not even going to write that one out. But this one's actually even simpler than what we had before, because that's not even there. We have something minus itself. We have 0. So p minus x is actually orthogonal to both our basis vectors. So it's orthogonal to the entire subspace. And that's all we need to show. It is actually orthogonal to that subspace. And it's in fact the only vector that we can get by taking p minus x to get something that's orthogonal to that subspace. That's what it means to be the projection. Alright, let's move on to problem 6. Here we again are talking about an orthonormal basis, this time for a arbitrary vector space V. We don't know what the vector space is or what these vectors are, other than that they form an orthonormal basis. And we're going to define two vectors, u and v, in terms of those. So this is just giving us our coordinates in the spaces for u and v. We want to determine each of the following: the inner product of u and v, the norms of u and v, and the angle between u and v. Now, because we have an orthonormal basis, we can actually calculate this as if we would, the same way we would if u and v were just vectors in R3. So remember what our coordinate vectors are. So if we call this E here, the coordinate vector of u is, well, 1, 2, 2. The coordinate vector for v, well, we don't have a u2 in there, so we have to use a 0 for it, but we have 1, 0, 7. And so all we need to do is take the inner product of these two. Or we could take the scalar product of those two. So uv is 1 times 1 plus 0 times 2 plus 2 times 7, and so we get a 15. It's just that simple once we have an orthonormal basis. Same thing, the norm of u is going to be the square root of 1 squared plus 2 squared plus another 2 squared. And so what do we have here? 1 plus 4 plus 4 is 9, so we have a square root of 9, or the magnitude is 3. Or norm, I should say, is 3. Same thing for v. We have a 1 plus 0 plus 49. We have the square root of 50. And I'm actually going to go ahead and simplify this because we're going to need it for the next step. We can pull a 25 out of that, and 25 is 5 squared. What we're left with inside there is a 2. So we have 5 square root 2. Finally, for c, remember we have this formula for angles. The cosine of that angle is the inner product over the product of the magnitudes. We have those values up from a and b. So inner product is 15. Then we have 3 times 5 square root 2. Well, 3 times 5 is the 15 that we have on top, so really this simplifies to 1 over square root 2. Or you might like this better as square root 2 over 2, if we rationalize it. But the point here is, what is the possibility for theta? Well, what angle was angle specifically between 0 and pi, or 0 and 180, that has a cosine of square root 2 over 2? Hopefully you know that one pretty well. It's either pi over 4 or 45 degrees, depending on which one you want to use. But that's all we have to do for that problem once we have an orthonormal basis. And that's why we like orthonormal bases so much. But let's actually step away from working with Rn. But we're not going to forget that we can actually work with things a lot more similar to Rn than we were in the past. So here we are going to look at this c of negative pi to pi again. Remember, we're using this inner product where we have the 1 over pi in front. And we recall that cosine of x and sine of x form an orthonormal set. They are unit vectors because of the 1 over pi, and they're orthogonal to each other. We're going to, well, they don't really explicitly state it out here, but we're going to be looking at the span of these two vectors. That is a subspace of c from negative pi to pi that has an orthonormal basis of cosine and sine. And the idea here is that we're given two functions, f and g, that are in that span because they're linear combinations of cosine and sine. We want to find the inner product of these two vectors. So how do we do that? Now, we could actually write this out as an integral. So 3 cosine x plus 2 sine of x times cosine of x minus sine of x. And then we could multiply that out. We'd have cosine squares, we have sine squares, we have sine times cosines. That could get a little bit messy to do that integral directly. But because we know that we can actually use this as an inner product, and we know that cosine and sine are orthogonal already, we can do this a lot easier. In this set, in this subspace, using this as our basis, well, f is literally just, well, f in coordinates at least is just 3, 2. G in coordinates is just 1, negative 1. So we can find their inner product by looking at the scalar product of their coordinates. We have 3 times 1 plus 2 times negative 1, and we get 1. This integral, if we were to work it out, would just be 1. Or if we don't have the 1 over pi here, this integral, if we worked it out, would be pi. So integration can be a lot simpler once we have this idea. Though we did have to do some integrals to get to this point, so we can actually work with that. But the point is that we can use the ideas that we already found to solve new problems easier than we did before. We want to do things the easy way. Alright, now on to orthogonal matrices. We have a matrix here. It's a 4 by 2 matrix A, and we want to first show that A is not going to be an orthogonal matrix because it's not square, but we are going to show that its column vectors are orthonormal. So how do we do that? Well, we could just do that directly. We could go ahead and just find. Well, let's name the columns. That might make it a little easier to work with. Let's say they're A1 and A2. We're going to look at what is the norm, or really the norm squared, of A1. A1 being 1 half, 1 half, 1 half, 1 half. So what is that norm? Well, we have the first one squared plus the second one squared plus the third one squared, fourth one squared. We have the sum of 4 1/4, so we get a 1. And in fact, the norm of A2 is very similar because we still have 1 halves, but finding the norm actually gets rid of the negatives. So very similar thing. But then we also need to figure out that these are orthogonal to each other. So what do we get if we take their scalar product? We have 1 half times negative 1 half, so negative 1/4. We have a 1 half times another negative 1 half, so another negative 1/4. But now we get a positive 1/4 and another positive 1/4. So specifically, these two negatives are the important thing. They cancel out these two positives, so we get 0. This matrix is orthogonal. Or well, sorry. Keep wanting to say it's orthogonal. It's not orthogonal because it's not square, but it does have orthonormal columns, and that's really the more important thing. We're going to use that idea to solve these least squares problems. We have this matrix A times x equals these column vectors B's, and we want to solve those easily. And we can do that. So this is part B, but then we have another A, B, and C. I don't know why they didn't pick different notation for that. So this is part B, part A. We're going to remember our formula for solving the least squares problem. As long as we know that we have orthonormal columns, well, x hat is going to be just A transpose times B. All we need to do is take the transpose of this A and multiply them to the B's. So here, our x hat is going to be A transpose, A transpose. In fact, I'm going to pull out the 1 half. If I pull out the 1 half of that, I have a column of all 1s. I have a negative 1, negative 1, 1, 1. When I take the transpose, that doesn't change the 1 half, and I can write that out a little easier. So I have this is A transpose times B. B is 4, 0, 0, 0. And I just need to form this matrix product. I'm going to leave out the 1 half for the moment, but we have 4 times 1 plus 0 times everything else, so we have a 4. And then we have the second row times that. We have a negative 1 times 4, and then 0 times everything else. So ultimately, we do just get 2, negative 2. That's our least squares solution. And we didn't have to find inverses or anything. It's just right there. Doing part B. Here we have a different vector B. It's 1, 2, 3, 4 instead of 4, 0, 0, 0. But the process is exactly the same. In fact, A transpose is exactly the same. Just we're multiplying by a different column. In this time, when basically we just add up the numbers from 1 to 4, we get 10. Then we're adding 2 and we're adding 3 and 4, but we're subtracting 1 and 2 from those. We're going to go ahead and get 4. And so ultimately we get 5, 2. Finally, part B, part C. Our x hat there is still going to be A transpose. But this time our vector is 1, 1, 2, 2. So what do we get this time? Well, now we're still adding up these numbers. We have 1 plus 1 plus 2 plus 2. So we get a 6. Then we have a 2 plus 2, but we subtract 1 and 1. We're going to get 2. So our answer this time is 3, 1. Let's use this to solve another problem. So problem 22, we're going to use the same matrix A from exercise 21. So this one that we have here. We're going to find the projection matrix P that projects vectors onto the column space. And then we're going to go ahead and use the solutions from part B, all of our least squares solutions, and we're going to calculate some things to show how those work, how that is related to actually the projection of our vectors. So let's start with our projection matrix. Remember, to actually show that A is an orthogonal, or that it has orthonormal columns, we looked at these inner products, and we essentially are showing here that A transpose A is the identity matrix, because this product just consists of this inner product, this inner product, this inner product, and then the A2 inner product with A1, which is the same as the inner product of A1 and A2. So this is a 2 by 2 square matrix that has these three and this one repeated. But if we want to look at the projection matrix, we're actually looking at the other direction. We have A times A transpose. This is not going to be a 2 by 2 matrix. In fact, it's going to be a 4 by 4 matrix. But it's actually not too hard to compute. So first of all, I am going to plot the 1/2 like I did before. So A is 1/2 times the matrix with the column of all ones, so a column where we have -1, -1, 1, 1. A transpose still has that 1/2, but now it looks like that. If we multiply that out, we do have a 1/4 out in front, but now we have a 4 by 4, and probably should leave myself a little more room for that. The first one is going to be this row by that column, so we have 1 plus 1, so we actually have a 2 in this first spot. And then we have this row times that column. Well, that's actually the same calculation. We still get a 2. Then we have this row times that column. 1 minus 1 gives us a 0. We get another 0 here. And then I'm going to kind of skip through this a little bit, just because there are 16 different calculations technically here, but a lot of them are very similar. The next row, we're using the same row from here, but then we're going over the same columns that we did in the first place. So we get a row of this 2, 2, 0, 0, then a row of 0, 0, 2, 2, and then 0, 0, 2, 2. And I'm gonna have to use up the rest of the page. This matrix gets a little bit big. So what do we have now? Well, we do have the 1/4 out in front still. We're going to have to divide each of these 2's by 1/4. So we could either just leave out 1/2 in front, or I'm just going to go ahead and put it inside. We have a 1/2 here, 1/2 here. We have actually a square of 1/2s, a square of zeros, another square of zeros, and then another square of 1/2s. But that is the projection of vectors in R4 onto the column space. Take any vector and multiply it by this by this matrix. We're going to project onto the columns of A. Now let's actually use that to do some calculations. We're going to take, they say the solution's x. These are the least squares solutions, so I don't know why they didn't put the x hat. So these are the x hats that we found in part B. We're going to multiply them by A, and then we're going to take this matrix here. This is our P. That's another name. That's another notation that we're using for our projection matrix. We're going to take this matrix P, and we're going to multiply it by the B's that we had before. So specifically, these B's that we have here are going to be multiplied by P, and these x hats are going to be multiplied by A. So technically, part B, part A, we have A times the vector 2, -2. Remember, that was our vector that we had here, 2, -2. And we want to remember what, I guess we should probably put A in here so we can, here. I'm going to copy A and P over to here. Okay, so here's my A and my P. I'm not going to write them down every time just because they are rather big matrices, but at least we can reference them as we do the calculations. So for part A, we have 2, -2 that we're going to be multiplying to A. So we have this 1/2 from A, but then each of these rows of A are going to have to be multiplied by this column. So we are going to have to do 4 different calculations. We have 2 plus 2 will give us a 4. We have another 2 plus 2 will give us another 4. Then we have 2 minus 2, so we have a 0 and a 0. So let me make this a little nicer. This will be 2, 2, 0, 0. On the other hand, we also need to look at P times B. Remember, the B in this case, well, I'll just write the B in here. Our B that we started with was 4, 0, 0, 0. So we're going to have to multiply this 4 by 4 matrix times this 4 by 1 column. Again, we're going to get a 4 by 1 column. So the first row of P times this column, so 4 plus 0 plus 0 plus 0. Then we have 4 plus 0 plus 0 plus 0. But now we had the only non-zero thing here is being multiplied by 0 in both of these, so we actually get 0 in those as well. So we again get 2, 2, 0, 0. What about part B? Now remember, here our result, our least squares solution is 5, 2. We'll go ahead and multiply that by A. So here we saw the 1/2, but then we have 5 minus 2, so 3. We have another 5 minus 2, so another 3. And then we have 5 plus 2, so we have 7, and then 7 again. And we could leave the 1/2 outside now because, well, we're just going to be getting fractions. We have 3 halves, 3 halves, 7 halves, 7 halves. But the vector that we actually started with, that we found the least squares solution for, was the vector 1, 2, 3, 4. We're going to multiply that that vector by p. So again, we have a 1/2 out in front. Then we need to take 1 plus 2 plus 0 plus 0. 1 plus 2 is 3. We have the same calculation for the next one, is 3. For the third one, we have 0, 0, 3 plus 4. 3 plus 4 is 7. We get 7 for that one as well. So, again, we got the same result as we did over here. I think you might see the pattern by now. We should expect the same thing to happen for C, and we just want to calculate it out. This time, our least squares solution was 3, 1. We're going to multiply A to 3, 1. We saw the 1/2. What is our 4 by 1 column? Well, now we have 3 minus 1, so we get a 2. Then 3 minus 1 is another 2. Then we have 3 plus 1 is a 4, and another 4. We can simplify that one. 1, 1, 2, 2. Now, what was our actual vector that we started with? It actually was 1, 1, 2, 2. If we multiply that one out, if we multiply that one by p, we have 1/2. We have 1 plus 1 plus 0 plus 0 is a 2. Then we get another 2 by the same calculation. Then we have 0 plus 0 plus 2 times 2 plus 2 is a 4, and then another 4. So we get 1, 1, 2, 2. So this is kind of the idea about what the least squares solution is doing in terms of the projection. The projection, we're basically finding the vector where when we multiply it by a, we get the projection of the vector that we were started with. That's the basic idea behind why this whole thing works. But there is kind of an interesting thing here where we started with the vector 1, 1, 2, 2, and we got the same vector 1, 1, 2, 2. What does that mean? Well, it's actually pretty simple. 1, 1, 2, 2 is already in the column space of A. Actually, yeah, I'm just here. A's up here. If we can actually find a linear combination of the columns of A to make this vector. Actually, what would we do? Yeah, I don't see it off the top of my head, but there is actually a way to actually write this vector as a linear combination of these vectors. That's what that means. So it's not as mysterious as you might have thought of. But that's got a little bit off topic. The point here is to show how we can use orthogonality to solve least squares problems and what that means. Alright, well, I'll leave that for now. In the next section, we will actually figure out a way to use this concept of orthogonality or orthonormal columns to solve least squares problems that are not that don't start with an orthogonal matrix or orthonormal columns by actually kind of forcing the columns to be orthogonal in a way. That might seem a little bit mysterious, but you'll just see when we get to it. But I don't want to get too much into it right now. So I'll leave that for now. I'll see you guys next time.